this. All right, you guys in the Discord, can you hear me? Cool, thank you. All right, Arya is not here today, so if you have a question, you have to speak up. All right, good morning, guys. Congratulations, made it to another Friday. Week's almost over. You know, the hardest part of my day yesterday was I bought a new DJI Mavic drone for a project that I'm working on. It came in yesterday morning. It arrived at my house in its box, and I couldn't play with it because I had like to finish the floating for assignment 3 and this lecture and a bunch of other stuff. But it was like it came in, and I was just like, it was like the most grown-up thing I've ever done in my entire life to be like, look, this amazing toy that I desperately want to play with. I'm gonna put it down, and I'm gonna do my homework. So, any questions, comments, concerns before we get started today? They are done. Yeah, they get posted today. They're done. I just got to do what's called reconciling them, which means I have to like physically hit the boxes, but it's all done. Yeah. No, time for us due next Wednesday. So Blackboard maintains a calendar. So when I update the due dates and stuff, or put a post assignments and stuff, all of that appears on a calendar on our Blackboard page. I should probably post like a better, more accessible link to that. Or it might even show up like in your like master, like total Blackboard calendar with like stuff from your other classes. But that's the best way. We are like, I need to just go delete the schedule from the syllabus because like we're way off that now. So I'm not sure I can like revise it. Yeah.
So like, when are we gonna start chapter 5?
When? Today, yeah.
So like the reading the textbook. What did you want to do? Chapter 5 section?
Yeah, okay, so we're gonna figure out a better way to do that. So yeah, so we're gonna start chapter 5 today. So I'm gonna swing my project over the weekend. I will get rid of the schedule on the syllabus because it just confuses people and we're lost now. I will come up with like a new sort of schedule and a system to keep it updated. Or at least we have like the next couple days of stuff on there.
Gotcha.
Yeah. So we'll create a dynamic schedule. But yeah, so we're gonna start chapter 5 right now. All right, any other questions? Yeah, so now we get unit 3 was due yesterday. Unit 4 is due next Wednesday. We're still targeting exam 1 for the next Friday, the 24th, and it will probably be due the following Wednesday. So, anything else? All right, let's get into it. So, up till now, we were working with Boolean algebra, right? We're making big expressions from our truth tables. We use those theorems and laws to sort of create those nasty expressions, try to get our optimized results. But I'm going to say this. There are 2 main problems. With Boolean algebra. Boolean algebra. That's hard. No joke, no way around it. Boolean algebra sucks. It's hard to do. And I don't even like, not even just like, oh, it's difficult, I don't memorize stuff way, but like, there's no systematic approach, right? There's no do these things. We tried to come up with one that was like, use uniting theorem, and then use absorption, and use elimination, right? But even that gets kind of wishy-washy. There's no systematic way to optimize algebraically. Right? It's hard. There's no systematic way to optimize algebraically. When you get a Boolean algebra problem, it's just soup. And there's no, like, you just got to sort of embrace the soup. Like I said, it's one of those things where if you have the time, pour yourself a drink, have a good time, sit down, relax, solve the problems. But if the assignment's due in 45 minutes, right, it's a little bit difficult to sort of get in that mind space. And so you need a systematic way to sort of, all right, I'm going to do this first, do this, I'm going to do this, and then I'm going to get my optimized result. Boolean algebra doesn't let us do that. It's too subjective. Problem 2 is that it's difficult to know if you arrived at an optimized solution. It is difficult to know if you've arrived at an optimized solution, right? So you've done all your Boolean algebra, you sort of run out of things to do. You've got this expression, you're like, I cannot think of any other thing to do this to this expression. Is that an optimized solution? Or do we still develop somewhere? Or do I just suck at Boolean algebra, right? There's no clear-cut way to know that we're done, and so or that we have an optimized solution. So those are the two main problems with Boolean algebra. Like I said, we do Boolean algebra when it's good, right? 2 is useful still. There are still times, even now, in our sort of 21st century society, to do Boolean algebra. Still happens in the industry from time to time. But also, you got to sort of pay your dues. This is the way they did things back in the 50s and 60s. They used to roll out big sheets of paper and write out the expressions and solve them out, do those big giant 256, 1024 row truth tables with big long Boolean expressions. That's how your forefathers did it. They put a man on the moon doing it. And you got to do it a little bit, right? So just to be part of the club. So, but there's a better way to realize. That better way is called a Karnaugh map. And specifically today, we're going to talk about 2 variable and 3 variable Karnaugh maps. K-A-R-N-A-U-G-H maps. These are K-maps for short. And this is the tool that we use to optimize our Boolean expressions. So the first thing we can do before we do K-maps in a serious way is we need to revisit binary notation. Right? We talked about it a little bit when we did the creating this generalized min-term expression, right? So the way binary notation works is that we have a function that is of a number of variables. Let's just use 3 variables, for example. Let's use 4 variables. And we got something like this. A, B prime, C, B prime 4, A, B prime, C, D. First off, let's revisit the old stuff. What does it simplify to? We can apply the mapping here, and then we get we're going to make a connection between paths. Yeah, they're not the same. But you know, it'd help if I wrote the correct expression on the board. B prime, C prime, D prime. No, you still should have been able to answer it then. It would have simplified to that one expression, right? But yeah. Now A, B prime, C, D prime, or A, B, C, B prime, C, D. Now let's simplify it. This should be a lot easier. What's that? Yeah, right. Now you can across the D variable gives us A, B prime, and C. Now underneath it, I'm going to go ahead and lay down that binary notation. Right. So if a thing is non-inverted, it's a 1. If it's inverted, it's a 0. And if it's not there, it's a dash. We'll talk about that, what that means in a second. So A, B prime, and C, and D prime is 1, 0, 1, 0. Or, now here's what's going to be really confusing, because we're going to use binary and the or, not an and, or not, excuse me, not an add symbol. A, B prime, C, D is going to be 1, 0, 1, 1. And that's going to simplify to A, B prime, and C, which is 1, 0, 1, dash. So let's deconstruct it just a little bit. If you look at the 2 binary notations, binary representations of the terms, what you're looking for is places where they're different, right? In the first position, they're the same. In the second position, they're the same. In the third position, they're the same. But in the fourth position, they're different, right? So there's 3 bits that are the same and 1 bit that is different between these two. So the first rule, right, can I write this definition on here? I don't know, order of complaining. So using binary notation, two terms will combine. All about uniting here now. Combine. And only at first if their binary notations differ by only 1 bit. Right? So if only 1 bit is different, then they'll combine. So let's say this. Let's do f is a function of a, b, c, d is equal to a b prime c or a b c. So we lay out the binary notation. Here it's important to note how many variables the function has because we got to know where our missing terms are. So our function is a function of a, b, c, and d. Even though these only have a, b, and c, we still have to keep track of what's missing. So that means it's going to be so a prime a, b prime c is 1, 0, 1 dash, or abc is 1, 1, 1 dash. So the question is, do they differ by only 1 term? Yeah, right? They differ by this middle term, which means that the result is going to be wherever they differed, that becomes the dash. 1 dash, 1 dash. And in binary notation, going back to our Boolean expressions, 1 dash, 1 dash for a function of a, b, c, and d is going to be just a and c. Hopefully you can already see the sort of advantage of this over Boolean algebra, right? Laying down the binary notation, you can like really quickly sort of look at it and see where places are going to combine and where they're not. Let's see, let's do another one. Let's do it. And also function of a and c. E is equal to a prime, a, b prime, c, d prime, or a, b prime, c prime, d. So in binary notation, that's going to be 1, 0, 1, 1, or 1, 0, 1, 0, 1. Will this combine? What's that? The next one? Oh, D prime, yeah. I think I say that every day of the week. On Monday, it's like, oh, it's Monday. Friday, it's Friday. On Wednesday, it's no excuses. Okay. So, yeah, so these guys combine. Now. All right.
Is A prime or not? Is A prime?
Yeah. What are you asking?
Well, the number of dash A.
There's a little smudge on it. Even if it was A prime now. How many bits are different? 2, right? That means don't combine them, we call them narrow. Now there's one other rule that usually only comes up when we do sort of subsequent versions of this. Any dashes must be at the same position. So I'm going to raise the top up here and do another example. So if we have this f function of a, b, c, and d is equal to a, b prime c, or a, b, d, that's going to be 1, 0, 1, dash, or 1, 1, dash, 1. So there's a lot going on here, but more to the point, the dashes are in different positions. This dash is in the D position in the first term. This dash is in the C position in the second term, which means even if for some other reason, like the bits were all the same, you still couldn't combine them. Make sense? So those are the 2 rules. Only 1 bit difference between the guys, and all the dashes must be at the same position. Cool. Any questions about that? All right. All right. So now, look at these. So, basically just is a box. All right. And that's the whole thing. Next, we need a truth table. Let's say we have A and B, 0, 0, 0, 1, 1, 0, 1, 1. And we have an output function f, which is at 1, 1, 0, 0. So the first thing we have to do is populate the K-map. So first thing is we take whatever our function is, f, and we're going to label that on the end of our stem there. The 2 variables, the a and b, are going to go like this. The first one, the leftmost bit, goes on the top. Second bit, the rightmost bit, goes on the bottom. And then we put in our, or actually, excuse me, then on the A side, we label the first column 0, the second column 1, and on the B side, we do the same thing, 0 and 1. So what's going to happen is inside these boxes is going to be the min term that sort of fits that definition, right? So this box is going to be 0, 0. This box is going to be 0, 1. This box is going to be 1, 0. And this box is going to be 1, 1. That's the basic set. That will always be the same no matter what the truth is. Cool? Any questions about that? All right. So the next thing you do is you take the columns, the min terms, and you go ahead and populate it. So we have a min term at 0, 0, 1. The min term is 0, 1. That's a 1. We have a max term at 1, 0. We're going to draw the 0. And a max term at 1, 1. We're going to draw 0. Now we populate the map. So all we're doing in the K-map is looking for places where those rules of binary notation adhere to each other, right? There's only one bit of difference between the terms. So for example, 0, 0 and 0, 1 has only one bit. In a two-variable map, most of them are the same, right? 0, 0 to 1, 1, 0 will combine, but 0, 0 to 1, 1 doesn't combine. Here's the important rule of K-maps. You're going to create groups that have to be powers of 2. What I mean by that is we're going to group these two guys together, right? They have to form rectangles, and they have to be of the size of the power of 2. So you could have a group of 1, a group of 2, a group of 4, right? You could have the whole thing filled out, but you could not have a group of 3. Does that make sense? All right. That's the thing that gets everybody, right? Has to be a power of 2. So when you group these, all we do is we look and see, okay, well, where does the column or the group sort of fit nicely in the K-map? So here you would notice that our column, our group here, fits inside the A equals 0 column, but splits B equals 0, and B equals 1, right? That means that B0 and B1, that's the term, that's the bit that's different, right? So from this, we would just say that F, function of A and B, and based just on this grouping, we would say it's just equal to A prime. Cool. Do one more. That's all there's to it, right? You're going to make groups. Let me change a little bit. I'm going to erase so I don't have to constantly redraw the map. Let me revise the truth table to this. That's not a lot you can do with a two-variable map. So 1, 1, 1. I'll put my labels back. 0, 0, 0, 1. So now I've got ones at 0, 1, and 2, and a 0 at 3. So 1, 1, 1, and a 0. Now I go to group again. And remember I said you can't have a group of 3 and you got to have a rectangle. So I can't just group all 3 of these in one shot. What I can do is group that one like before. That gets us A prime. And then I can group this one, this top row, right? That splits A equals 0 and A equals 1, but fits nicely inside B equals 0. So that means we have or B prime. So all you're going to do is you're going to look at your truth table, you're going to populate your map, you're going to create the groups. Write down.
So how do you guys push it on the,
I could not understand anything you said.
why do you get us which one's prime?
What do you mean?
Like by 1 to 0?
So look at B prime, right? The group that we used to make B prime was inside B equals 0.
Okay.
That's why it's B prime.
Oh, and then 1 would be B.
Yeah, if it was down here, right? If the group was here, where B equals 1, then it would just be B.
Okay, that's what I thought. But
Yeah. All good. All right. That's really all we said about two variable maps. Any questions before we go on to three variable maps? All right. Three variable K-maps. All right, let's start with the truth table. Three variables. A and C. Yeah. Dropping everything down. let's say we start with 0, 0, 1, 1, 1, 0, 1, 0. All right. A 3-variable map is like a two variable maps sort of stacked on top of each other. We're going to draw a big rectangle. Order it, put it half top to bottom, and add our step. Whatever. All right. So now, just like before, we looked at our truth table and we populate our map. We've got F, the leftmost bit still gets to go on top for A, and then we'll combine B and C down here. Just like in the 2-variable map, the A gets labeled as 0 and 1. Now the B, C column, or the next 2 variables, will get labeled in a similar manner, but it's tricky. We're going to go 0, 0, 0, 1. Now we have to, the next row has to be able to combine with this row, so it can only differ by 1 bit. So what we're going to do is say 1, 1, and then 1, 0. There we get that. So if we were to label the min terms inside the boxes, we would say 0, 1, 3, 2, 4, 5, 7, 6. All right. Now we populate the min terms and max terms. We've got 0, 0, 1, 1, 1, 0, 1, 0. And like before, we set out to make.
How did you come up with the 0, 1, 3, 2, 4, 5, 7, 6?
Well, I didn't come up with it. Karnaugh came up with it.
Oh, okay. I thought it was just
Yeah. The catch is because the bits have to be the same, right? So if I did this in binary, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, like every adjacent cell has to meet that rule of only being different by 1 bit. Right? So here 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, right? So if you look at each.
oh, they're all binary numbers.
Yeah.
Okay.
Cool. So we're going to solve this one. Right in here, F, function A, B, and C. And let's see. Here's what we're going to do. One thing that you can notice is look at 4 and 6. Right? 1, 0, 0, and 1, 1, 0. Are those adjacent? By adjacent, I mean, do they only differ by 1 bit? Yeah. So that means we can combine those two. And what would that get us? Any guesses? Just C0. So notice that everything in the group is inside, everything in the group is inside A equals 1, so we know it's going to be A. It also is in C equals 0 and C equals 0, but it splits B0 and B equals 1, so that means, it's going to be A, C0. And then last up, we can do these guys, which is going to get us in the A equals 0 column, so A naught, and it's in B equals 1, but splits C equals 1 and C equals 0, so it'd be A prime and B. Any questions about that? What's up?
Could you go over the last bit again, where you got like C naught?
Yeah, so you look at, we make our group, right? We're looking, for the first one, we're looking at these guys. We group them from top to bottom. So with this one, 4 and 6. Now, if you just did it the way we just did it with binary notation, that's 1, 0, 0 for 4, or 1, 1, 0 for 6. We look at the bit that's different, right? This one is in the B position, so we know that's going to be equal to 1 dash 0, which is going to be A and C naught, right? So that's why, but like visually, if you look at it, you've got C equals 0 here, and C equals 0 down here. And then B equals 0, and then B equals 1 down here. You look and see which variables don't change. So you make a group and you say, all right, A is A equals 1 and A equals 1, right? So I've got A. And then you say, all right, B is 0 and 1, that's different, so B is out. And you say, all right, I got C is 0 and C is 0, those are the same, so that stays as C prime. Does that make sense?
Is that the volume?
Yeah.
Not group 2.
Ah, so we could group 2 and 6, but that wouldn't give us the minimal solution, right? Once groups are already covered, right? The goal is to create the smallest number of groups as possible. Yeah, so once you, and in fact, what would that term be? What's that? Yeah, because B and C naught, and that's kind of hard to read down here. Just gonna erase this 2 here. What do we have? We have F equals A, B, C equals A and C prime, or A prime and B, or B and C prime. What is that? That's the consensus term, right? So yeah, so the fact that these guys were already covered, it's kind of what we mean by consensus terms are redundant, right? These are already covered by these two guys. So if you combine them, if you cross the streams there, that term you're going to get is going to be the consensus term of those two terms. So yeah, so there's no need to make groups or make terms of variables that are already covered by the terms. Otherwise, there's going to be consensus terms. All right. What about I can drop two. Okay. All right. What about this? I'll write the zeros. What can we do with this guy? Has to be rectangle. It also has to be of size and its power of 2. Yeah. We can make a group of 4. We box all of them. And what's that going to give us? Oh, stupid. You're absolutely right. I just wrote wrong. Try again. Yeah, it's B, right? Because it splits between C equals 1 and C equals 0. Splits between A equals 0 and A equals 1, but fits neatly inside B equals 1. So yeah, just X equals B. if I just did this. Cool. That's cool. All right. What do we get from that? Good. B and C not, right? Because it fits, so we're going to make root 2. All right? Splits 0, A equals 0 and A equals 1, but is inside B and C not, right? Sort of in that row altogether. So yeah, F equals B and C not. All right. Let's do a trickier one. What if we didn't have a truth table? We're going to like reverse engineer it. We started with a relatively simplified expression, something like this. F function of A, B, and C is equal to A, B, and C prime, or B prime C, or A prime. Now we have to kind of reverse engineer the K-map. So let's start with the easy one. A, B, and C prime is what? A, B, and C prime. Well, that's just one single minterm, right? Where's that going to go? What's that? It's going to go in 1, 1, 0. It's going to go to this bottom right. Oh, he's like slowly like amplifying it. All right, does everyone see what happened? We were looking at this term, A, B, and C prime. And now where is that in here? And yeah, it's going to be A, B, and C prime. It's going to be 1, 1, 0. So it goes in the box for 1, 1, 0. What about the next guy? B prime and C. What's that? Yeah, it's going to be across the second row. So that's going to be dash 0, 1, right? So we look there right A, 0, 1, so that means 1, 1, right? In reverse, as if we had drawn a group around those terms. Now what about A prime? Yep, all the way down the A equals 0 column. Now we're going to draw, if we've already drawn one, we don't need to draw it again. And there you go. And I guess you can draw the 0 rows. One last thing. Any questions about that? Yeah, so we can look at an expression and reverse engineer. So I'm going to draw 2 canyons next to each other. start solving that one. The answer is both the same. It's going to give me a grouping for what are these? What's that?
Top left, 1, 1.
1, 1. What do you mean?
Grouping.
Be more strict. I don't know what you mean. So I eliminate a term that groups cells such and such and such.
The chapter group 0, 0, 0, 0, 1.
The busy. Yeah. Okay.
Could you group 0, 0, 0 so that it would be pairs? So, not the top of the bottom.
Yeah. Do that. Okay. So this left-hand side one. What does that get us? Yeah, it's a prime V1. All right, now this one gets us what? Yeah, that's it. Okay. Now that we've done that, we're kind of locked into our solutions for both of these maps now, so let's just keep them going. On the left-hand side, what can we do? The bottom row. It's going to get us what? What else? What's that? Yeah, these two left. What will that give us? I guess ECE. That's it for the left-hand one. What about the right-hand one?
Could you do 01 yeah, there's
yeah. That'd be 0, 0, 1, and 1, 0, 1. What will that give us? Yeah. And there's one lesson. Perfect timing. This one? That's going to leave us with A and B. All right, so what happened? Yeah, so we have the exact same starting point. We have two different maps, we solved them in different ways, but we got solutions that are equivalent to each other, right? By all metrics, these are the same. Both of these returned. Terms 1, 2, 3, and 1, 2, 3, 4, 5, 6. Literals. 1, 2, 3, 4, 5, 6. 6 literals, right? So these are equivalent solutions. One little product from the other. Yeah, right? So this illustrates that last point, which is in Boolean algebra, like first off, for expressions, it is possible for there to be more than one equivalent solution. But when you're just doing the Boolean algebra, right? It can be typical to get here, know that that's, you're going to be haunted by the fact this other one is sort of hanging out there. You don't know what it is. With the K-maps, even though it can still happen, you can still know that you got like an equivalent solution, right? Because like I said, the goal is to create the smallest number of the largest groups possible, right? So we still have, this is 3 groups of 2. You can sit and look at this map for another hour. There is not a better way to lay this map out. You can lay it out that way, but it's still equivalent. It's still 3 groups of 2. So visually at a glance, you can look at it and be a little more confident that you have an optimized solution. And if you don't, you just take a look at the map again. A good rule of thumb that I always do is when I finish optimizing with the K-map, even if I'm pretty sure that I got the optimized solution, I always kind of take a look at the expression and think to myself, is there any Boolean algebra I could do here to simplify it further? Just as like a last little idiot check for myself. And hopefully usually the answer is there is not. All right, any questions, comments, concerns? All right, in that case, that is all for today. Like I said, Unit 4 assignments due Wednesday. The exam is going to be next Friday. I will work on a better, more dynamic way to update the schedule so that you guys can stay, those of you guys who are doing the readings can stay up to date with the readings. For now, just remember, for Monday, remember, we don't have class on Monday. So, because of the job fair, right? Go to the job fair. You should go to the job fair, unless you already have a job lined up. You should still go to the job fair, even if you already have a job. Who knows, you might get a better offer. So on Wednesday, we will finish Chapter 5. So we did like sections 1 and 2 in Chapter 5. We will do the rest of Chapter 5. So make sure you just have read all of Chapter 5 by Wednesday. Except for the 5 variable K-maps. We're not going to do this. You don't have to read the 5 variable K-map one, yeah. As if you looked at, I looked at it and was like, I don't want to do that. You got to draw cubes. Yeah, you have to draw a 3-dimensional K-map. It's a fun scholarly exercise, but we're not going to spend any class time on it. I'm certainly not going to test you on it.